So I'll just kind of step through them, and if you have questions, ask. But like I said, the sheet I gave you has these. So we talked in the previous chapter and this chapter about water's 3 physical phases. We have solid, liquid, and gas, and kind of that little drawing. And I brought my thing here. That little drawing right there. Yeah. Actually, that thing connecting the water molecules is what we call a hydrogen bond. See, hydrogen bond. It's the thing that connects the water molecules. Okay, so that's my point there. The next 2 terms kind of go together. Remember that humidity is water vapor that's in the air. I'm going to kind of dim these lights a little bit. Water vapor in the air, that's humidity. And 2 ways to kind of, they call them ratios to kind of take a division. Is that, do you have enough light there, Kay?
That's already better.
Okay, good. So the 2 ways we talked about is both of them has massive water in the top, or the numerator, but we talked more about mixing ratio, didn't we? Mixing ratio.
Do we need to memorize both of them?
Used more. I think mixing ratio will do ya.
Mixing ratio?
Mixing ratio will do ya, yep.
Okay.
Mixing ratio, just recognize it's this one. It's the mass of water, remember kind of like we did those little figures, divided by the mass of dry air.
Okay.
And then the next one, I brought in a figure from your textbook over here. So this actually talks about saturation. The figures before this, basically you had a dry and you had water evaporating, and then you had water evaporating and some condensing. But at saturation, you have remember we have 5 that are evaporating and 5 that are condensing. So that's saturation. So, and then this little thing up here, this is a little pressure gauge that's actually measuring, in this case, the water vapor, as those water vapor particles hit that gauge. That's we call it the equilibrium vapor pressure. So those things. Relative humidity, that's another way, an important way that meteorologists talk about. And of course that's percent relative humidity. So 100% means the air is saturated. So what you do, this table, it's hard to see, but this table actually is the saturation mixing ratios. So basically you kind of come along a temperature like this is, this looks like it's maybe 5 degrees, and this 5 here means that it can hold 5 grams of water for every kilogram of dry air.
Well, we need to know this on the test.
You might need to know this, I think in general. How do you get relative humidity? You take the actual water vapor, and actually I can't, all of these actually, I kind of tried to distill the test down to all of this stuff, so I don't really want to say you don't need to know any of this. So relative humidity, how much water vapor there is, you measure that, and then in the bottom you get it from the table. And then usually people come to this class saying that warm air holds more water vapor, and they're right. Actually, this saturation table right here, as you increase the temperature going from the bottom, going from the top down, actually you increase the water vapor that it can hold. So that's the trend. Warm air holds more water vapor. And then dew point temperatures. That is the temperature you need to cool the air down in order for it to become saturated, dew point temperature. Reach 100% relative humidity. And then this was actually a homework question where I asked about when would you best to water your lawn. Over here, when is it best to water your lawn? So in the morning, about 6 a.m., it's your highest relative humidity. And then actually in the heat of the day, it's your lowest relative humidity because warm air can hold more water vapor. So assuming you didn't put any more water vapor in there, you're farther away from saturation when it's warm. So humidity goes down.
So you would want to water your lawn early in the morning,
right?
Like I thought.
Yep. Hygrometer, that's just something that measures humidity. And then kind of related to that, a Sling psychrometer, you think it would be called a Sling hygrometer, but Sling psychrometer is the thing that we used in lecture.
In class.
Yeah, in
with
class.
The sock.
Swung around.
Yep, exactly, with the sock. You're both right. And we wetted this one and we slung them around, a Sling psychrometer. And remember that, which one got cooler, do you remember?
The sock.
The one with the socket cooler. Yep, exactly. And then we talked a lot about adiabatic cooling. That was the adiabatic base. So I kind of said, what's the difference between diabatic and adiabatic? And diabatic means you have a chunk of interest, and diabatic means you're basically adding heat across the boundary. You're adding heat to it or taking heat away from it back to the environment. And like, yeah, when you heat a pan of water, that's diabatic. But now adiabatic was basically when a chunk of air rises, it expands and cools. That's an adiabatic process because it's just that chunk of air doing it.
So adiabatic is no heat exchanged with the environment.
Yep.
And diabatic is heat exchanged with the environment.
Exactly.
So remember that.
Yep.
Star that.
Well, all of these probably a star, but and kind of related to that, if a chunk of air cools as it rises, it can cool to the dew point temperature. It can cool to the point of 100% relative humidity. And that elevation where it reaches 100% relative humidity because it cooled is called the lifting condensation level. So the elevation to which air lifts and cools to its dew point temperature. And I think I kind of answered both of those there.
So the LCL is the point at which the air rises and reaches the dew point.
Exactly. And then we had some three-letter things like ELR, DAR, WAR, okay? WAR. So ELR was the weather balloon. Yep, temperature of the atmosphere. With increasing elevation. And then the DAR, now that is what we've been talking about a chunk of air rising and cooling. That's the DAR, chunk of air rising and cooling, assuming it's just dry and there's no condensation. And that's about, and I'm trying to think, I don't think there's no math problems per se, but there kind of is, that last page, there's kind of a think about it question. It's not really a math, kind of like you had homework. But we said it's going to cool 10 degrees Celsius for every kilometer it rises, as long as it's not condensing.
For every, how far it rises?
1 kilometer.
1 kilometer.
1 kilometer, 10 degrees. 1 kilometer, 10 degrees, yep. And then if there is condensation, then we move from the DAR to the WAR. So W stands for wet. So wet adiabatic rate assumes that we have condensation going on. And so it is actually then when condensation happens, it's going to release a little bit of heat. And so instead of cooling at a rate of 10, it cools at a reduced rate of 5 or 6. That's where your author had 2 of those. It just slows down its cooling. And then the 4 lifting mechanisms look like this. Over here, kind of this, all I did was just kind of copy it from your textbook. Or from my notes. Here's the 4. We have the mountain thing, orographic lifting. We had the front things, frontal wedging. And we have convergence, air coming together and kind of lifting where it meets. And then we have kind of the hot spot, like something's like a dark color, and the sun heats it a little extra, and it it's localized convective lifting. So those are 4 ways. And then we talked about the 3 different types of stabilities. Now you send up your weather balloon and you get the ELR. You send up your weather balloon and then you compare the ELR to those other things. So if your environmental lapse rate, your weather balloon says it's less than the wet adiabatic rate, okay, then that is absolutely stable. Or absolute stability, absolutely stable, absolute stability. Okay. Now, if you send up your weather balloon and it's your lapse rate, your ELR, your environmental lapse rate is pretty high, greater than 10, then actually it's going to be unstable, absolutely unstable. And then if it's between the 2, it's going to be conditionally stable. And the condition I put over here is, do you have any moisture in it? So. Any questions?
That really helps to see it written out that way.
That I think so too, with the inequalities. Okay, on to chapter 5. Looks like this. So we have another 3-letter kind of acronym. CCN stand for Cloud Condensation Nuclei. And this is where, like, usually like a little piece of dirt in the atmosphere is the first thing to go ahead and get water to begin condensing. Cloud condensation nuclei. And then I couldn't remember if you need this for your test or not, but we talked about 2 different types of nuclei. Ones that love water, those are called hygroscopic, and ones, the word phobic means fear of. Ones that are afraid of water, those are hydrophobic.
That's why you put a heart in a sad face.
Yeah.
Great diagram.
Yeah.
Makes it easy to remember.
And how clouds are classified. So we talked about, they call it form. You know how I say flat or fluffy? They call that form or appearance. So flat or fluffy, of course, flat or stratus, fluffy or cumulus. And they're also here in red, I said, if they're low, middle, or high elevation. And then also here in purple, are they precipitating? So kind of 3 different things. How clouds are classified. And then I went ahead and brought in a figure from your textbook down here. There's 10 cloud types here. So here we kind of have the low, the middle, and the high. You can see the 2 precipitating clouds. Okay. You can kind of see the fluffy clouds here, 3 fluffy clouds. Remember, this is about the size of your fist, about the size of your thumb, about the size of your pinky. So I think you're going to want to know things, though, like when I say general description, like which one, you guys remember which one is like mare's tail?
Cirrus.
Very good.
I'm going to get a good grade on the cloud.
I hope so. You like clouds?
Yes.
Which one's like I call a mackerel sky, like a fish mackerel sky?
I can't say that I
It's one of those 2 in the 2nd column from the right.
It's the
Go to your left.
It's this one, the cirrocumulus.
Yeah.
Yeah, cirrocumulus, mackerel
Okay.
sky. Very good. Next one, lenticular clouds. Those are associated with mountains, and they're the big hovering, they look like a contact lens, kind of upside down. And they're sometimes, because of their shape and because they hover forever, sometimes they're called in as UFOs.
So it'd be like a regular stratus or an alto stratus?
Hadn't thought about it, probably, yeah.
Well, I mean, look at them.
Yeah.
They're the
Probably-
ones with the odd shape.
Yeah, very good. I'm kind of thinking alto stratus, but I don't know. It might be kind of between those 2.
Well, if it's stratus, I mean, it's lower to the ground.
It is lower to the ground if it's stratus.
So it would have a better chance of being over a mountain.
Yeah, but mountains are pretty tall.
So then it could be an alto.
But if it's over the mountain, it's close to what I would call the ground,
Yeah,
even though...
up there.
Like in the Smoky Mountains, I bet it's a stratus because the mountains are not that tall.
Okay,
And
I see all what you're saying.
Yeah, so.
And kind of like what you're saying, you guys are saying too, is they say the air gets pretty dry when you're going here, very dry up here. So there'd be more moisture closer to the, so I like that.
We should make that an extra credit question as we came to the review.
The next one, remember we talked about the first 2. Here we have, let's see, what would this be? This looks like rain. Okay, because remember it starts out as snow and it melts. This actually is snow.
It's
And
cold all the way down, right?
Cold all the way down, yep. And then these 2 have the pink in the middle where actually the snow melts and then refreezes down here. And these 2, that whole cold air in the middle, warm air in the middle, that's called a temperature inversion. So this is actually, the fact that there's room here to pelletalize, which one would this give you?
Sleet?
I'm liking sleet for this, and then what's this?
Freezing rain. Because it melts, but it's still not cold enough for it to become sleet or snow.
Right, there's not enough time for it to refreeze.
So it's just freezing rain, but it's the most dangerous.
It is the most dangerous.
Trust me. I have driven in freezing rain before, and I have witnessed plethors
That's not good.
of car crashes on my way back to college last year.
Not
It was
good.
bad. I mean, because in Tulsa we get freezing rain and ice. It's not cold enough
You're-
to snow, but it's cold enough to freeze over.
Yeah.
That is why it's
And you
deadly.
can't see the ice on the road.
Some roads. I mean, you have to kind of.
Assume it's there.
And because Tulsa's an oil city, it's even worse because of the moisture of the oil makes it that much slicker. Like after we've had a drought and it rains, there's at least 5 or 6 car crashes that have already happened within the first
Just
10
from
minutes.
rain.
Just from rain. Because the oil makes
That's
the road is very moist at all times, and when the rain hits it, that's extra moisture from all that drought. You have crowds.
That's how it is in San Diego and El Centro, California, which is out in the desert.
It'll
Whenever it
happen.
rains, because of all that accumulation of oil and dust
It's
and
slick.
stuff, as soon as the rain hits it, it's like,
Well, I mean, the reason it is like that in Tulsa is because the refinery's right there, and we produce a third of USA's oil.
Does it get better like after the rain, like a half an hour into a rain event? Is it better?
It gets better after a day.
Interesting.
Because when we get rain, we get rain. We don't just, it gets you here. We
That's
get
interesting. Fog. Wait, yeah. Types of fog look like this. So I have some pictures of the types of fog. Yeah. Radiation, advection. This is upslope, kind of like.
Like up a mountain.
Yep. Kind of like orographic lifting. And this one is the one. This would be. Let's see. This one would probably be called. Well, evaporation fog, but probably steam fog.
Yeah.
Yeah.
There's
kind
a
of on
bunch
your-
of names for that fog.
Yeah,
Let
a bunch
us
of names
know.
for that one. Supercooled water is when water is a liquid at a cooler than 32 degrees Fahrenheit. And then this one, so this actually, these two columns here show if you have water vapor that is in the vicinity of supercooled water and ice, notice that the water vapor is going to go ahead and build the ice crystal, because the ice crystal is what we call supersaturated with that water vapor. And here it's not. So your ice crystal, like we kind of saw here, your ice crystal grows and your supercooled liquid water particles get
And
little.
you showed us how
smaller.
much bigger the snowflake got as the water particles shrank.
Exactly. Yep. That's kind of a subtle thing. And collision coalescence, that happens in warm clouds. So basically they collide, a big one collides with little ones because it's going faster, and it gets bigger. Yep, that's collision coalescence. And then I can see it went on to the next one. The next one is hail. So one of the things I'm hoping you guys differentiate hail from this guy. This cannot give you hail.
No.
This gives you hail.
Yep.
Yeah, so I'm
I've
really
always
hoping.
known that.
Good.
Well, when you go to Oklahoma, like when my little sister's like, "Oh my gosh, it's not supposed to be snowing." I was like, "It's not snow, that's hail." We're about to get a tornado. Usually a tornado follows very shortly after.
yeah, 'cause-
Sometimes during a tornado you have hail.
Yeah, because
Oh,
this
yeah.
will give you your thunderstorms, lightning, hail, strong winds, and potentially tornadoes. Yep.
I would call that the curious cloud, because it's always curious what it's going to do to you.
I like that. Cumulonimbus clouds.
The curious cloud.
Okay. Cloud seeding, let's see what I did for that. Basically, it kind of goes up here. We said cloud condensation nuclei. You go ahead and sprinkle those in your atmosphere, hoping to get condensation to begin. And then these two phenomenon, Virga and fall streaks, are very similar. Basically, a cloud is dumping, but the precipitation doesn't reach the ground.
Okay.
And so you can kind of see it's dumping, but it won't reach the ground because the air is so dry. And you had a homework question about that, about the air has to be dry. This would be, I believe this is Virga and this is fall streaks. So this is rain and this is snow.
I have a photo in my photo collection of Virga.
Oh, cool. I look forward to that.
Okay, so. Nah, never mind. It's fine. Go ahead.
You sure?
Yep.
Okay.
On to 16.
Okay, so 16, you guys haven't seen it yet. We're going to roll through that here today in just a little bit. But chapter 16, when it says white light, it's kind of like what we've been talking about in the previous chapter, that when the sun sends radiation, all those different types of light, the white light coming from the sun actually is composed of red, orange, yellow, green, blue, indigo, and violet. That's my point there. Anybody says, I'm shining white light at you, well, that white light has all of those colors in it. That's my point. Yep, totally. And then we're going to talk about reflection. So if you look at a mirror, basically, this is your image right here. It hits the mirror, and that image is reflected back. So it's called the law of reflection. Basically, this angle right here is equal to this angle right here. Law of reflection.
A 90-degree angle.
Well, it
shows a 90-degree angle. It means 45 and 45. 45 is equal to the other 45.
Yeah.
Okay.
But I think, to me, though, if this one had been coming in here, okay, that would have made this angle longer, and actually it would have been coming back here. So it's not always going to be 90 like it's shown there.
Okay.
But they are equal.
So your reflection always comes off equal.
Right. Yep. Equal
Unless
angle.
you're in a funky mirror.
That's true. And actually, that's coming. We'll talk about that in lecture.
Okay.
But yeah. So there's a couple of ours. That's reflection. Now, refraction is different than reflection, but refraction gives us a lot of cool, different kind of things in the atmosphere. What refraction is basically, now this is not a mirror, okay? This actually is light going from air, and then light is going to now go into what we call a different medium. That kind of dark blue is water, so it goes from air to water. And can you kind of see it bend? Okay, so that's refraction. It's bending of light. Why? Because it's going to a new medium. It goes from air to water. It changes its direction. It takes a, okay.
What is it about the water that changes the direction of the light ray?
It has to do with, it's funny because I didn't think about this till recently, but you know how we talked about the speed of light? Oh, the speed of light is like 186,000 kilometers per second. Well, that's in a vacuum. How fast light travels in air is slower, and how fast light travels in water is even slower. So actually that kink, that turn, that bend has to do with light slowing down. And they call it actually the refractive index of the material. Like when you go to buy a diamond, they'll talk about the refractive index of the diamond. Basically, how does it slow light down as it goes through?
And then they also talk about how they're real. They can tell if they're fake. You can tell.
Our daughter, she got married about over a year ago, and they got a fake diamond, and it just looks beautiful. She's going into chemical engineering, so I thought, well, that's quite appropriate. But it's because of speeds. So refraction, light slowing down, and as a result, it bends, and we'll talk about why that is. But, yep. So internal reflection's kind of a fun thing. This is actually the cutest picture in this chapter, I think. Internal reflection. So light is going to reflect or bounce back off of, I say, the boundary. Light bounces back off the boundary between two mediums. So up here we said these were two mediums, air and water. So again, we have water and air. There's air above these chicks. Okay. So basically, light, there's the boundary right here. You can kind of see the top of her head. So light bounces off, reflects off of the transition point between the water and the air and comes back down. It's internal reflection. Is that not cool or what?
That is way cool.
It is. It's adorable too.
It is so interesting to learn the reasons behind phenomenon I've seen. You know, as a kid playing in the pool.
You can relate to that? Yeah.
Okay.
Okay. The next one, again, we're going to talk about this today, but so I said these are two medium. I said air and water are two medium. Well, that's pretty obvious. Air and water are two substances. But also two mediums or different mediums is just in the air. Remember you guys told me the air gets thinner as you climb up a mountain? So up at the mountain, the air has this sort of speed that light would travel through it. And down here, it's thicker, and it travels at a different speed.
I mean, it's not just going up a mountain, it's elevation differences. Like the girls from Colorado it took them 2 weeks to adjust finally to our elevation.
Really?
Really.
Oh my goodness.
We had a girl that had a headache for like 3 days.
And that's because she's going to an oxygen-rich environment from
Not so much oxygen.
yeah.
And when she came back, when she was running in the gym, she's like, I could hardly breathe. It felt like my lungs were going to collapse.
Oh my goodness. 2 weeks though, huh?
Took them 2 weeks to get adjusted.
Well, so light travels differently up there than it does here, and so we have an opportunity for refraction there, and it's kind of a subtle refraction. But here, actually, the sun is actually here, and the sun's light is bent or refracted down towards this observer. So the sun is really here, but if you take the last bit of the trajectory of the sun, we are going to think it's up here. So this says the sun's apparent position. You can't see it, apparent position, and this is where it actually is. Okay. So the sun is really down there, but it looks like it's up here.
Okay.
And so actually that can make our, the sun will kind of have set, and yet its light is kind of refracting up and around at us. So that's kind of an interesting thing. Our days are a little bit longer than you think.
Mirages. Oh,
Mirages.
I've had a mirage before. No, my coach was psychotic at my last school. He would make us run when it was like 110 degrees outside, because we're like in almost to the panhandle of Texas, and it's technically it's a desert. And we were running, and I had my first mirage. I saw ice cream sundae and ran and tried to eat dirt. And my teammates, Cassie, we've only been out here for 30 minutes. How are you having a mirage? I was like, because I'm not like this. I don't run like this in this kind of weather.
Yeah.
That's not fair.
I think that might be something different than this. Well, it is kind of like this mirage. This mirage, though, everybody would see. It's not because you're fatigued or anything like that. But everybody would see this mirage. So it's not an ice cream stand or anything. But just because of refraction. And here, actually, we kind of see the refraction of light. Now, these two mirages I'm going to show you are both caused by temperature of the air. So
also, when it's like the pavement is super hot and the sun's hitting it, and you think you see something, but it's not.
Yes, kind of along those lines. If the pavement is super hot, what you're going to do is see actually kind of an image of the thing on the horizon. You're going to see it down below, and it looks kind of like watery.
Yeah, it's usually, I'm thinking of
I see that all
the
the time
times
when I'm
I've driven
driving
through the desert, and it looks like 3 miles ahead because the road's flat as can be. And it looks like I'm going to be driving into water.
Yeah. That is
an
an inferior mirage. Yep, these are inferior mirages. This is a superior mirage, which I've never seen one of these.
What are they?
Superior mirages happen when, again, it's the temperature of the air, but it's like really cold here, and it gets warm, cold air, and then it gets warm above it. It's a temperature inversion. And so a superior mirage, notice that you have an image also, but now it's above the horizon, so it's kind of like floating above the horizon. I'll show you a picture in class today.
Okay.
Yeah.
Okay, and then optical. Ooh, rainbows and halos.
Yeah, why are there so many? And so this is the last slide in chapter 16, and it's a table from your textbook, and we're going to talk about various things. And this last column says what causes them. So if you look up rainbows occur because of reflection and refraction. It's coming up here in a minute. And because of the presence of raindrops, from kind of a distant storm petering out. Rain droplets are causing it. So you're going to want to know, we'll talk about rainbows today, something called a halo, corona, sundogs, glory, sun pillars, and green flash. So you're going to kind of want to know what causes them, what particle causes them.
Which is it? I was driving yesterday and looked up at the sun, only I couldn't see the sun, but I saw this image that I could almost see through, but not quite.
Okay. That sounds like an altostratus cloud, maybe? Like a wisp, like a thin cloud.
Could have been,
Yeah.
because
The
I was
sun could have been
driving and I
projecting through
couldn't
it.
stare at it
Yeah.
very frequently.
So, yeah, that's kind of what it sounds like. Then that actually concludes our review session. Wait, is there one more? Oh, yep. I brought in rainbows. Conditions needed for a rainbow. Remember, I think I had you add that to your review sheet when I gave it to you on Friday. So 3 conditions, kind of. You need the sun low on the horizon. The sun needs to be at your back. And like you told me, kind of a rainstorm will bring us a rainbow. So what's happening is the rain clouds are probably moving this way, probably, and there's kind of suspended liquid particles, okay, that actually is allowing for light from the sun to be first refracted and then reflected back off the back of the mirror and kind of refracted one more time.
Love your diagram.
What's that?
Love your diagram.
Thanks.
I do too. It's stick people. I can work with stick. People. I don't like the whole fancy stuff where you like, how did they draw that? That's an
Yeah.
iPad. You can't.
Well, very good. Well, if you have any other questions, let me know. But thanks for coming.
When is chapter 16